So, in the last lecture I had briefly introduced three different ways in which we can perform experiments on X-ray diffraction. So, let us look at the first method called the Lavie technique. Now, in this technique, basically what we are doing, we are going to vary the wavelength while keeping theta fixed with respective HKL planes. So, the incident beam hits different HKL planes at a fixed value of the Bragg angle theta. So, now here obviously, so this is a crystal out here, this is a basically fixed crystal, it is not moved, it is not rotated, this is my incident X-ray beam. So, with different HKL planes, this incident beam will be making some very specific incident angles, and these are all the scattered beams. Now, incident X-rays, let me remind you, is a white radiation. So, therefore, it will have a range of wavelengths. If you look at X-ray spectra of the white radiation, it is something like this. On the horizontal axis, it is the wavelength, and out here is the intensity of the beam. So, there is a certain value of wavelength below which there will be no X-rays, and let me just call that as lambda minimum, though it is also called as lambda SWL, short wavelength, and let us arbitrarily fix some lambda max. So, I will have a variation from lambda minimum to lambda max. Beyond this lambda max, the intensity is very small, so we will not be able to observe any scattered beams. Now, this is one kind of geometry in which the X-ray beam is going through a thin crystal, and therefore, this geometry is also called as the Lavie forward reflection. This is another geometry called as the Lavie back reflection geometry, in which essentially this is my incident beam. The crystal is thick, it cannot go through the crystal, but the planes reflect them backwards. So, these are all the scattered beams. Now, let us try to understand this geometry in terms of the reciprocal lattice space. So, let us try to see this. I have drawn, basically this is a reciprocal lattice, the red dots represent the reciprocal lattice points, and I have drawn two spheres, and O is the origin of the reciprocal lattice, A is the center of the smaller sphere, and B is the center of the larger sphere. Now, what are these two spheres? These two spheres also, as I described it in the earlier lecture, are spheres of reflection having a radius of 1 upon lambda. Now, here we have a variation in the wavelength. So, the smallest sphere that we can get will be having the radius of 1 upon lambda max, and the largest sphere would have a radius of 1 upon lambda minimum. In between there, you can imagine that there are lots of other spheres of varying radius of 1 upon lambda, as lambda varies between lambda minimum and lambda maximum. So, now for example, let us see which possible scattered beams we can get. This represents the incident beam for the smaller sphere, S naught upon lambda max. Now, I can get a scattered beam wherever the reciprocal lattice points are intersecting the sphere of reflection, and in this case the smaller sphere. So, I can get a scattered beam here, I can get another scattered beam here, and so on. Because why will I get a scattered beam here? Because if I join this point O and let us say this is point P, then the scattered beam vector or the scattering vector S divided by lambda max would be a reciprocal lattice vector. Similarly, if I look at the larger sphere, I can my incident beam direction is the same, obviously. I will have a scattered beam out here, let us call this as point Q, another scattered beam out here, call this as point Q prime, and similarly I should also call this point as P prime. So, I have scattered beams on the larger sphere. Now, what about other values of the wavelength? Well, in between the volume of the smaller sphere and the larger sphere are all of these reciprocal lattice points. They will all lie on one or the other spheres of reflection which will be having some specific wavelength. Therefore, all these circled points that I have drawn would produce a diffraction. So, for instance, let us say this point R out here, this lies on a sphere of reflection whose center let us say is somewhere here, and let me call that as point C. Then I will get a scattered beam in this direction because it is lying on a sphere of reflection with some specific wavelength, and this scattered beam direction, if I call it as unit vector small s upon some lambda, where this lambda is in between lambda minimum and lambda maximum. So, you can imagine that all of these circle reciprocal lattice points will be lying on one or the other spheres of reflection. So, all of these would produce reflection, or all of these will satisfy the diffraction conditions. So, that is why you will get number of scattered beams. Now, coming back to this figure, this is a recording media which record the position of the diffracted beams as spots, and this is the these two are the X-ray diffraction patterns or the Laue diffraction patterns. This is for forward Laue and this is for backward Laue. Now, interestingly, you also find that the diffraction spot, for example, in the forward Laue, you can find groups of diffraction spots which lie on ellipses. This is one of the ellipse that is already drawn. Another ellipse perhaps can be this one, and maybe we can extend this something like this, and you can find other groups. Similarly, in the backward Laue, here is a set of points which is already and a line has been drawn through those points. This is a hyperbola. So, these spots are lying on hyperbolas, and you can locate other hyperbolas as well. maybe something like this. So, you can find other hyperbolas on which the diffraction spots are lying. Now, I am not going to prove this here, but the spots lying on ellipses in the forward lavae and spots lying on hyperbolas in the backward lavae, these are all spots from planes of same zone. Now, what does this mean? Recall the zone wise law. Now, the zone wise law states that HU plus KV plus LW would be 0 if the direction UVW lies in the plane HKL. Now, all the spots which belong to the same zone means that there is a direction which is common to all of these planes, and that is why they are called spots lying on the same zone. These assist us in indexing the pattern. So, any analysis of diffraction patterns from X-rays requires indexing. Now, what does indexing means? That we have to associate HKL indices with the individual spots. So, we have to find out from which HKL planes we are getting reflection. Once that indexing is complete, then one can find out using this Lave technique, for example, the orientation of the crystal. Now, here one thing to note, that these diffraction spots are actually what? These diffraction spots are nothing but the reciprocal lattice itself, because after all, when you are indexing, you are just trying to find out what is the HKL index of the spot which corresponds to the reciprocal lattice point with the HKL index. So, these diffraction patterns are actually nothing but the reciprocal lattice itself. So, you can see there is a tight relationship between the reciprocal lattice and diffraction. Now, this is not all that straightforward to index typically Lave techniques, but I just wanted to briefly indicate that such a technique exists. Now, let us go to a second technique. Here we are shooting monochromatic X-rays, which means X-ray of a very specific wavelength, and the crystal itself. So, this is my crystal. The crystal itself is rotated, and that is why this is called the rotating crystal technique. Here theta is varied as a result of this rotation, but as I had indicated, not all possible values of theta are possible in this technique. Let us see how we can analyze this technique using the reciprocal lattice. So, let us say that I have a sphere of reflection. This is my incident beam S naught upon lambda. This is the origin of the reciprocal lattice. So, let us say this is my reciprocal lattice. Now, when the crystal is rotated, the reciprocal lattice also will rotate. So, for example, if I consider this particular reciprocal lattice point, it may intersect the sphere as it rotates about this axis, and it may intersect at various locations on the surface of the sphere, resulting in scattered beams forming a kind of a cone. And you can imagine, as the rotation occurs, there will be other lattice points which will also be intersecting the sphere at different locations as the crystal is rotated, because the reciprocal lattice also rotates along with the crystal. And that is how you get several diffraction beams in this rotating crystal technique. This is my recording media. And this is the diffraction pattern obtained. Again we get spots, and it is also mapping, each spot is mapping out a reciprocal lattice point. Each layer, so you can see these spots occur in layers here, and these layers are occurring because the reciprocal lattice is rotating, and you get, so for example, this is a specific layer that will be observed on the recording media as diffraction spots. Using this, one can determine structures of unknown crystals, particularly crystals with low symmetry. Now we come to the third one, which is the most popular technique, and we will spend some more time on this third technique. So, this is a photograph of a X-ray diffractometer. There is a, this is the X-ray source, and again we use monochromatic radiation. This is the X-ray detector, and out here is the sample. Now, there are couple of geometries that are used in X-ray diffractometers. One geometry could be, you can imagine that there is a circle which is essentially this circle I am talking about, and the X-ray source and the X-ray detector can move on this circle. Now, there are a couple of geometries. One geometry is that this is, let us say, the sample, out here is a source, out here is a detector. So, this is the incident beam, this is the scattered beam, and this is the sample. The angle of incidence with the surface of the sample is theta, and the angle of reflection is also always kept as theta with the surface of the sample. Out here is a detector. Now, one thing that we can do is what is called as theta to theta geometry. Here the sample and the detector is rotated. The detector rotates about this circle, sample rotates about its axis in the center, and the source is kept fixed. So, S is fixed here. Now, in order to keep the angle of incidence and the angle of reflection same with the surface of the sample, if sample rotates by theta, detector D has to rotate by 2 theta. Now, this you can check, is very simple to check out this geometry. This will ensure angle of incidence and the angle of reflection are always the same. So, by this rotation we can get angles with different HKL planes. So, we can vary the angle and the wavelength is kept fixed. The second geometry is called the theta theta geometry. Now, in theta theta geometry, the sample is kept fixed. However, the source and the detector moves by equal angle theta, and that is why it is called the theta theta geometry. So, here source S and detector D moves. Now, what kind of a diffraction pattern I will get? Essentially, the detector is measuring the intensity of the X-rays at different values of the angle theta, and this is how one would get the diffraction pattern. The horizontal axis is not theta, but it is kept at 2 theta, and this is the intensity of X-rays. So, for specific values of theta, you get these peaks where diffraction is taking place. So, we know from this directly that at what angle we get diffraction, the Bragg condition is satisfied and there is no extinction. Now, we keep this as 2 theta is only basically for historical reasons. So, I have, let us say, these are my HKL planes. This is the incident beam, this is the reflected beam, this angle is theta, this angle is theta. Now, if I extend this incident beam, then the angle between the incident beam and the reflected beam is 2 theta. So, the instrument is recording this value of 2 theta, and this 2 theta is sometimes called as the scattering angle. So, from this diffraction pattern, now what we can get are different values 2 theta 1, 2 theta 2, 2 theta 3 and so on. And from this we will do an exercise in the next lecture to find out what is the crystal structure for the material. Now, I also, before concluding, I also want to say a few things regarding the sample that is used. Now, in this case, what we have used is a polycrystalline sample. This is the surface of the sample. Now, what is a polycrystalline sample? Well, polycrystalline sample consists of each one of these is a grain which is nothing but a single crystal. So, each one of these small cells that one is looking at is actually a single crystal, and each of these crystal is randomly oriented, which means that the HKL planes which are parallel to the sample surface would be different for different grains, and hence in this way one is able to get different incident angles with different crystals when the wavelength is kept fixed. So, in this case we are able to get essentially all possible angles with different HKL planes, and of course, not all of them are going to reflect because the Bragg's law will not be satisfied for all of them, and therefore, we get these many diffraction peaks, and these are the peaks where some of those HKL planes have been and the incident beam is at a very specific angle, so that the Bragg's law is satisfied, and that is how you get so many diffracted beams. Now, in the next lecture, what I am going to do is I am going to take the same diffraction pattern which has been obtained from this X-ray diffractometer to analyze that diffraction pattern in terms of the crystal structure. And finally, if one looks at it, this is a video of this same diffractometer, and you will see the source and the detector will move, as I had explained, in a theta theta geometry. There you go. The source and the detector both are moving in such a way, and the sample is fixed, so that the incident angle and the reflected angle is the same. Thank you.